Hello everyone, thank you for joining. My name is Dijkshoorn from the Robotics and Mechatronics group at the University of Twente. And today I would like to tell you about our research on in-situ monitoring of layer-wise fabrication by electrical resistance measurements in 3D printing. 3D printing sensors has a large potential at the moment. However, the sensor performance depends heavily on the print quality. For this, sensors are currently characterized after fabrication. However, in-situ monitoring is desired, is favorable. What we did is that we performed electrical resistance measurements during printing, so in situ, to monitor the resistance. And in this way, it allows us to get a better understanding of the printing process. So the effect of every layer added on the sample, the effect on the resistance can be measured in this way. And this can also be used as a proxy for measuring print quality. For the measurement principle, it's based on standard electrical resistance measurements where electrical contacts are either placed on the printing bed or in one of the first layers of the sample. And when the nozzle extrudes molten conductive polymer, the change in resistance can be measured. And ideally, every layer added to the sample aids in lowering the total resistance. One of the challenges is the positive temperature coefficient of conductive polymer composites. Since below the melting temperature of these materials, they have a positive temperature coefficient. So when the temperature goes up, the resistance goes up. So during printing, during the print phase, as you can see in the figure, the resistance goes up. And then after cooling down, during the cool down phase, you can see the resistance going down to a lower value. For the methodology, we printed small samples of 4 by 4 centimeters with 6 layers, where every layer is 1/4 of a millimeter thick. We've used a direct drive extruder to print both conductive PLA and conductive TPU, thermopolyurethane filaments, which are filled with conductive carbon black particles. As electrodes, we use copper tape, 2 pieces of parallel copper tape on the sample or in the bed. Furthermore, we've performed finite element method simulations to better understand the effect of adding layers with both resistivity and the interlayer contact resistance, since with printing the different layers can have a contact resistance depending on the print parameters. For the results, you can see in figure 3 the resistance over time for conductive PLA for different print settings. And you can clearly identify the different layers, added layers, by means of the periodic peaks with the heating up and the cooling down of the sample. The peaks for the different infills can be seen give a different result. So printing parallel to the electrodes gives sharper, more pronounced peaks than printing perpendicular to the electrodes. Furthermore, if we compare the measured resistance per number of layers to the finite element method simulation, we can see that added layers for a large number of layers with the interlayer resistance don't make a big difference. However, for samples without an interlayer resistance, adding layers keeps on lowering the resistance significantly. All in all, the Neuvel method shows change in resistance per layer, and it has a strong qualitative similarity for different materials, different print settings. And this method allows for optimization of the print parameters to optimize electrical conductivity in 3D printed sensors and structures. The measurements and the finite element method simulations do not fit well for small numbers of layers. This probably can be explained by a poor connection between the electrical contacts in the print at the start, giving a high contact resistance, which is lowered when the printer heats up the material, anneals it, and pushes it together onto the contacts. This was my presentation. Thank you very much.